Okay. So there are 8 questions for this tutorial. So the time should be not that enough. So we start now. And so the first 4 questions might cover the Bernoulli equation and also the energy equation. So for the first one, it's a venturi section pipe which developed low pressure that could draw the fluid from the reservoir to the nozzle. So, and there is assuming there are no friction loss, it wants us to derive expression for the exit velocity V2. In this question, we suppose that the atmospheric pressure is PA, and the pressure at outlets is P2, which is equal to PA. And we suppose assume the liquid, the fluid in the reservoir and in the venturi section are the same. So they are the same liquid. So using this, we also know the diameter of the pipe D1 and D2 at the two positions. So we assume that it is a steady flow and also incompressible flow and also inviscid flow, which is no friction loss. So we could apply the Bernoulli equations based on the assumptions, right? So the first of all, the most basic principle we use is the continuity equation, applying on 1 and 2 positions. So position 1 and 2, we apply the continuity equation first. Because it is incompressible, so we use the continuity equation for the volume flow rate. So for the volume at position 1 is the velocity V1 and the cross-sectional area, which is equal to, that's V1, that's V2, D2 squared. That's the continuity equation, right? So we can easily get the expression for V1. So V1 is be expressed by this. Okay, and then we know the pressure, we know the velocity. We apply the Bernoulli equations at these 2 positions. So at position 1, the Bernoulli could be written as P1, which is the pressure, static pressure at position 1, plus half rho V1 squared. V1 is the velocity. So that one is the Bernoulli on the right, on the left. And on position 2, it's P2 plus half rho V2 squared. Yeah? And now we know that the water, the liquid, was drawn from the reservoir to the pipe. So we know the fluid, the pressure of the fluid here, which could be written as, the P1 could be written as PA minus rho GH. Yeah? And then we put these things, the pressure P1 and P2 we got from the question, atmospheric pressure. So we put all this into the Bernoulli equation, and we can find PA minus rho GH plus half rho V2 square D2 D1 power 4, which is equal to PA plus half rho V2 square. Yeah? Put all things in. Let's put 1, 2, 3. We put 1, 2, 3 equation, Bernoulli equation. And we got the terms of, and also all the row of. So we can get V2 is square root 2g8 over D2 over D1 square power 4 minus 1. So for this one, we know the flow is, we assume the flow is steady and incompressible and inviscid. So we could apply the Bernoulli equation as the link of each parameters. And also the basic principle, the continuity equations, is also applied. So we use these two to get the expression of V2. Yeah? Question? Okay. So the next one also is also very similar to the first one. But what difference is that in the nozzle, it is air. So the air going through the nozzle, so which generates the pressure difference and makes there's the height difference. It is not clear here. The height difference of oil. The oil in the pipe makes the height difference of the oil. And also, there's no viscous loss. So, and also the steady flow, so we could apply the Bernoulli equation as well. But I have a question. So we noted position 1 and position 2 here. So if we want to get the pressure at position 1, at the stagnation point, what kind of pressure it is? It's a static pressure or stagnation pressure? Stagnation pressure, yeah? Because all the pressure here hits the pipe and then make it the stagnation point. So the pressure we generated is stagnation pressure. So actually the height difference, the 8 centimeters height difference, cut by the difference of the stagnation pressure at 1 and the static pressure at 2. So firstly, we apply the Bernoulli equation, which is P1 plus half rho V1 square, which is equal to P2 plus half rho V2 square. Yeah. And the left hand side, that one, the P1 plus half rho V1 square, that one is its stagnation pressure. And P2 is static pressure. So we now know the pressure here and the pressure here. So we got the difference. So P1 plus half rho V1 square, which is the pressure at the left-hand side pipe, minus P2, which is the pressure at the right-hand side pipe. The difference gives the raw oil GH, gives the height difference. And then we know the diameters of the nozzle. So the second one we could link is applying the continuity equation as well. We suppose that because the flow is very slow for the air, we assume that it is the incompressible flow. So based on the continuity equation, V1, the cross-sectional area A1, which is equal to V2 d2 squared. We got the relationship of this. We link these two. So we could solve that one first. So the P1 plus half rho V1 squared minus P2 is rho oil GH, which is the specific gravity, and rho water, which is Pascal. Firstly, we solve this, and then we could get this is also equal to half rho V2 squared. Yeah. So we can get V2. We can get V2, which is equal to the 2 multiply the pressure difference we got over the density of the air, 1.2. Could solve it, V2 squared. So we can solve the velocity at position 2 meter per second. So we got the V2. And once we got yeah.
Isn't V1 0?
V1.
Because it is a stagnation.
No, it's just like I could explain it to you that. So what I've written here is the general velocity at V1 here and here. So what I've written is based on the point that is not the stagnation point. Just like because the Bernoulli equations, the pressure in the Bernoulli equations are all static pressure. So if we, for example, there's a pipe and we got the pressure tap here, the velocity here, and here are V1. That is not stagnation. But the velocity, only the velocity here is 0.
Then can we take our reference point as that point to make it easy? To get rid of all the V1s.
Yeah, you can. You can just let me see.
Because I think it ends up being the same.
Yeah, yeah, you can. You can just say that that one is stagnation pressure P1.
Yeah.
So you can use the P1 star, that is stagnation pressure,
Yeah.
minus P2. We got rho oil GH.
Yeah, exactly.
Yeah, you can use that. That one is equal to P1 plus half rho V1 squared. Good. So when we got V2, we could calculate the volume flow rate, which is pi for V2 squared, V2 0.3 cubic meter per second. Yeah? Okay. then you need to make sure what is the stagnation pressure and what is the static pressure for this question. Okay, so we move on to the next one. In this question, we know that the water are absorbed by the pipe, and it is absorbed in the pipe and going out of the pipe from the reservoir. And we assume that the area of the reservoir is large enough. So what does it mean if the area of the reservoir is large enough?
I mean, the pressure's constant because it's not dropping.
Yeah, it's not dropping, and the surface steady.
Yeah, it's
yeah.
almost constant.
Yeah. So I want us to get the outlet velocity Vx, and also the pressure at the top of the pipe. So firstly, and also we know the height difference. So firstly, we can apply the Bernoulli equations from each point to each point. You can choose the velocity. You can choose the point from point 2 to 3, and apply the Bernoulli equations. But the problem is the velocity of the fluid at position 2 are the same as the velocity at the 3. So when we apply it, the velocity will be declined. They are the same. So we couldn't use it to get the velocity. So we need to find the other place to get the velocity. But we know the surface 1, because it is large enough, the surface will not move, which means that the velocity up here is 0. So from here, we apply the Bernoulli equation from 1 to 3. So for the 1, we just write it, the P1 plus half rho V1 squared plus rho G H1. So now we take the exit, the position 3, as the datum, which means that we take this place, the height is 0. So, which is equal to P3 plus half rho V3 squared plus rho GH3. So now, what is P1? It's linked to the atmosphere, right? So it is P atmosphere, and for 1, the velocity is 0. So the second term is 0 plus half rho 0 squared plus rho G. So the H1 here is H in capital, which is equal to the pressure at outlet, which is also the atmosphere pressure, plus half rho Vx squared, which is the terms we want to solve. And the height here is 0 for the position 3. And then we could get the Vx is square root 2g capital H. So we use this, we choose the static point to the moving point to get the velocity of the exit. And then we need to solve the pressure at the top. So we apply the Bernoulli equation again from 1 to top point. At 1, which is P atmosphere plus 0, the velocity is 0, plus rho gh. And at the top, which is the pressure, we would like to solve the half rho Vx squared, because the velocity in the pipe are all the same based on the continuity equation, which is and plus rho g. Based on the datum, the height here is capital H plus L. So now we can get the P is P atmosphere pressure minus rho g H plus L. We put the Vx into this one. Yeah? Any question? So we need to choose which is the beginning of the point and which is the final point we need to apply. We need to choose 2 points to apply the Bernoulli equation. Okay. So move to the next one. It said that a pump water from the lower reservoir to the higher one, which means that the pump work will provide the work to move the water to balance the height, and also it said that it has the total head loss, which means that it has the head loss due to frictions along the pipe. But what we could do is to assume the flow is steady, which means that the velocity are the same along the pipe, and also adiabatic because of no heat transfer, and also incompressible because it is water. So from point 1 to 2, it has the friction loss, so we couldn't use the Bernoulli equation, right? But we can use energy equation instead. So now we apply the energy equation and write it in the head terms. It means that for one, the P1 over rho g plus V1 square over rho g plus Z1, which is the energy at position 1, and plus the pump head, which is equal to the P2 over rho g plus V2 square over 2g plus Z2, and plus H turbine, the turbine work, and plus the head loss. So that's it, a general term of the energy equation. Yeah, but I write it into the head terms it gives us the head. So now we analyze which terms we could remove. So at position 1, because of the reservoir too large, so we could remove the 2 kinetic terms, which means that the velocity which means that the velocity are the same and it's 0. To remove that, so that one is we could reject. Yeah. And also the P1 and P2 on the surface are all linked to that atmosphere. So P1 and P2, so P1 is equal to P2 is equal to atmosphere pressure. So that 2 terms are the same. Yeah. And then there's no turbine. So the turbine work is 0. It's 0 here. And also, if we take the position 1 as datum, which means that the Z1 here is 0, because we take that one as the datum. Z1 is 0. That one is also 0. So we finally got the pump work. The pump head is equal to the Z2 plus the head loss due to friction, which means that the pump only provide the work which would balance the height difference, the head caused by the height, and also the head caused by the friction. So which means that it is the 2 is 100 and the head loss is 20. So we got the pump head here. So once we got pump head, we could use the definition of work to calculate the work output from the pump. So now we calculated the work output from the pump, which is the mass flow rate multiply GH pump. Yeah. And the mass flow rate is rho Q, the density multiply volume flow rate, GH pump. And we got 1000 the volume flow rate. So we got the work output from the pump. But it is not the work input to the pump, because the pump motor have the efficiency. So due to the definition of efficiency, which is the work output from the pump over the work input from the pump, the work input from the pump, that gives the definition of efficiency. So we can get work input, which is equal to the work of the pump, work output from pump is over the efficiency. Yeah. Which gives the final result here. So in this question, we need to know how to apply the energy equations into application.
Is Is that going to be kilowatts?
Oh, sorry. Yeah. It's kilowatt. And then you need to know the efficiency, the definition of efficiency. Okay. So up to now, I've given the 4 questions using the application of like the Bernoulli equation and the energy equation. So next, we might go to the shear stress. The shear stress one. So the air at 20 degrees forms a boundary layer near a solid wall of a sine wave-shaped velocity profile. Because it is have viscosity on the wall, so the profile form the shape like this. And the boundary layer thickness is 6 millimeters. This is the thickness of the boundary layer. And the peak velocity, you know that the peak velocity here is 10 meters per second. And it wants us to calculate the shear stress tau at firstly at the wall, near the wall. Why? Yeah.
Can we actually solve this question by like the wave equation or something?
Yeah, you can use the wave equation.
Is it the way to solve this question? Is it? It's weird.
What do you mean? Sorry.
Like the wave equation is sine wt plus
Yeah.
phase. Can you use it in this question to solve it?
Yeah. We just get the wave equation, and then we just put all the y.
Values.
Yeah. And also the velocity at the 3 meters, the shear stress at 3 millimeters high and 6 millimeters high. So we got the sine wave shaped velocity profile. First of all, we need to solve it. So we know the maximum, the peak of the velocity is u max. So we could write the equation to u max, because it's a sine wave, sine pi y over 2 delta. The delta is the thickness of the boundary layer, which is 6 millimeters. And then, based on the definition of the shear stress, which is mu partial u over partial y, so we can put the velocity profile into the definition, and we got the tau is mu u max, the partial sine over partial y, it is pi over 2 delta cosine pi y over 2 delta, based on the profile function. And now we could solve the tau at different heights. So at y is 0, we got, firstly, y0, we got tau is mu u max pi over 2 delta, because y0 cosine 0, so the cosine 0 is 1. We finally got back in here 1.8 multiply, which is the viscosity, multiply 10, multiply pi over 2, which is 0.8 0.047 Pascal. So first we got the y, the tau, the shear stress at y is equal to 0. Second one, at y is 3 millimeters. We saw that the tau is equal to mu u max pi over 2 delta cosine pi over 4. So which is 1.8 multiply 10 multiply pi over 2 just it. And then for y is equal to 6, which means that the cosine, the terms in the cosine are pi over 2, so it's 0. So we got twice 0. Yeah?
I didn't understand like the first part of being determined in mu is equal to u max sine pi over 2 delta.
You don't know how to get this.
Like, yeah, like the first one.
Yeah, because we know it is a sine wave shaped, and the sine wave reaches the peak at the delta. Yeah. So it should be that we put the delta into the terms in the break of the sine, and we got pi over 2. Because for the sine wave, we got, it's pi over 2, we got the peak. So the sine terms here should be pi over 2. So if we put the delta into the term, we need to get pi over 2. Okay? More questions? Okay. So move to the next one. Okay, finally we got this one. I remember in the first tutorial we solved the question which is similar to that one, or the same as that one, but we can solve it again. I can give you like 2 or 3 minutes to think about how to solving it. That could be a little bit challenging, but it's not that difficult. It's not like the question in last tutorials with the weak one. It's not like that one. And it should reach the difficulty of your final exam. It says a disk rotating in the oil, and it forms a viscous layer around it. No, it's the disk rotating in the. Yeah, put the rotational disk in the oil, and it forms the velocity profile, which is linear. any idea of this one? Okay, so in this question, wants us to get the moment of the torque. So the moment should be written as the force multiplied by the distance to the rotating center, right? And the force is the viscous force. So the shear stress will generate the viscous force. So the viscous force, definition of it is the shear stress multiply the area. Yeah. And then we need to solve the torque, the shear stress. So firstly, we know that the velocity is the linear profile, which means that the torque, the shear stress, partial u over partial y, we could return it. For example, we gave the clearance, that height is h. We give that one is h. So, and at the top of it, it reaches the maximum velocity, which is u. We make it as u. So this is mu, because it's linear, it is equal to u over h, because the velocity here, it is linear, so we can use the u over h. The u is the velocity at this position, and the h is the height of the clearance. But now we don't know the u. The u is, we need to solve the u based on the radius and omega. The rotational speed multiply the radius. So which is mu omega omega r over h. That is the torque at the position. So for the plate, for the disk, at different radius, the torque, the shear stress are not the same, are different, because of the radius are not the same. Because we get the definition, because the equation of torque is linked with r. We just put draw the disk out. This is the rotating center, and from here, this is the radius. So the shear stress at this point, and the shear stress at this point, and the shear stress at this point are not the same, because the radius are not the same. So what we need to do now is to apply the integration. Because of the radius are not the same, the shear stress varies along the radius. So we take a very small, take the infinite part here, which has the radius r, and the length of it is dr. Yeah. So we can solve the shear stress at this radius which means that the torque here at this radius is mu omega r h at this position for this infinite one. And then we could solve the force, the viscous force at this radius. Means that we solve the so at the ring of the infinite part with the same radius, the viscous force should be the same, right? So the area here, because we need to multiply the area, so the area here, dA, should be the dr multiply the length. The circuit's length of this. Yeah? It should be 2 pi r. That gives the area here. And now we could get the dF, which is the viscous force. The dF is torque multiply dA, which is mu omega r h 2 pi r dr, which is mu omega h 2 pi r square dr. So we got the dF here at these small rings. And then we could solve the torque, the moment of torque here. So the dt in this on this radius should be r multiplied dF. Yeah. So which is mu omega 8 over h 2 pi r power 3 dr. So finally we got the moment for this infinite part. And then we do the integrations from the radius of 0 to the radius of r. Because it has the two surfaces, we only solved one. So we got the t actually is twice 0 to r dm. Yeah, that one is dm, sorry. Yeah. So which is twice 0 to r mu h 2 pi r3 dr. What we got is pi mu omega r power 4 over h. We multiply 2 here because it has two surfaces. We do integration twice to calculate the torque, the moment. Question of this one? It used the sorts of integrations in this question. Okay. So if you got the question of this one, you can ask me later. So now we solved the shear stress one. And the last two are using the coefficients of lift and drag. For this one, as a field attached to the string is put in the wind with the velocity of u, and it is blow up and generate the angle here. So, and we know the drag coefficients CD, and also the density of the sphere, and also the